And now we're back one last time for one more way that we can understand the binomial coefficients. And in this time, we're going to do it with generating functions. So what is the generating function? Well, we call it f of x. The definition is just going to be the sum, k greater than or equal to 0, in choose k. Here I'm thinking of n as fixed, and I'm interested in tracking that parameter k. So I'm taking the generating function with respect to k for some fixed n. And what I want to do is I want to prove to you the following theorem, which is known as the binomial theorem. It explains why these are the binomial coefficients. F of x is the binomial 1 plus x to the n. Okay, and that's why this is called the binomial coefficient, because they're the coefficients that show up when you expand this out. So let's see why this is the case. And let's do it with our example that we had before, where we had n equal 4. Okay, so when n equals 4, we can think of, we have 4 choices to make. We can choose the red dinosaur or not. We can choose the orange dinosaur or not. We can choose the green dinosaur or not. And we can choose the blue dinosaur or not. So here, what are we going to say is 1 equals don't take it, and x equals choose. Okay? And so the coefficient of x to the k is equal to the number of k element subsets. Because if you just think in this example, if I look at what's the coefficient of x squared, in exactly 2 of these, I get to pick the x for the dinosaur. And in the others, I have to choose the 1, right? And we saw that the coefficient of this in 1 plus x to the 4th, we saw that was equal to 6. And maybe let's write that out. Excuse me, dinosaurs. So what are those coefficients? When we expand it out, we get 1 plus 4x plus 6x squared plus 4x cubed plus x to the 4th. So that's what our generating polynomial, it's a function, it's also a polynomial in this case, looks like. And so we can see that the coefficient here was 6. And that's just from writing that out. But we have this nice combinatorial way to understand it. But let me write these coefficients again in sort of, this is the 4 choose 0, here's your 4 choose 1, here's our 4 choose 2, 4 choose 3, and 4 choose 4 is also 1. Now, there are some interesting properties we can derive from this formula of the recurrence relation. There's some interesting identities that we can write down. So one of them is the following. We notice that the sum from k greater than or equal to 0 in choose k is equal to 2 to the n. So in this example, 1 plus 4 plus 6 plus 4 plus 1, that's a 5, that's a 5, that's a 6. This is 16, which is 2 to the 4. Why is that the case? Well, it's the case because really what we're computing is f of 1. And if we look at this form of saying f of 1, that's saying, yes, we're computing this sum. And now on this side, we're just saying 1 plus 1 to the n. And so we can see that that identity is true. Here's another identity that's kind of interesting. I think it's a little more interesting. So minus 1 to the k in choose k is equal to 0. Again, let's look at this example. 1 minus 4 plus 6 minus 4 plus 1. The positive terms, I got a 1, a 6, and a 1. Negative terms, minus 4, minus 4. It's 0. Why is it 0? Again, look at the generating function. This is just f of minus 1. It's minus 1 to the k. So that's what we're plugging in for x. So that's kind of a nice identity. A corollary is that the sum of k even of n choose k is equal to 2 to the n minus 1. Why is that the case? Well, we know the sum of k even, that's all the positive terms, is equal to the sum of k odd, because that would be all the negative terms. So they have to be equal. So they're each exactly half of the total. And this is half of the total. So there are nice properties once we have the generating function. There are nice properties that we can derive, nice combinatorial facts that we can prove, and then we can look, once we have the identities, we can look to get a combinatorial proof of the identities, which would be kind of neat to have. And then there are more sophisticated ones that we can get using more sophisticated generating function techniques.